Welcome to 6C. You're encouraged to come to the front of the room. Please do. So I think without further ado, we're going to go ahead and get started. Our first speaker is remote, Macarena Lagos, and we're starting with gravitational wave lensing for massive black holes. So go ahead. Can we switch it so we see her?
Thank you.
There we go. Okay, perfect. Take it away.
Okay, thank you so much. So in this talk, I would like to tell you about the rates of how many events we expect to see to be gravitationally lensed in LISA in the next decade. And this work is based on this paper here on arXiv, in case you want to know more details. So gravitational lensing is a general phenomenon when you have a signal traveling from a source to an observer and it is encountering some massive object like a galaxy along its path. And a strong lensing in particular happens when you have a very good alignment of the source, here a binary system, the lens and the observer, in which case there can be multiple paths that travel from the source to the observer. Effectively, in the case of gravitational waves, this translates into the fact that you would detect multiple repeated signals that actually come from the same source. They would arrive at different times and with different magnifications, but the overall waveform is expected to be the same. Strong lensing in electromagnetic observations has been, well applied to cosmology, to learn about dark matter and constrain, for example, the expansion rate of the universe. So, what do we expect regarding lensing for gravitational waves? So for the current detectors, LVK, rates estimate that we expect one or a few strong lensed events per year in 05. There's already some discussion that there's some maybe low evidence for one event being already strongly lensed, but that's still debated. But at least in 05, we'll be lucky to confirm with high confidence the first strong lens event. Now, for Einstein Telescope and Cosmic Explorer, because just the general observation rates are so much higher, we do expect to have 100 strong lens events per year. So this will become commonplace in the next decade, and it's important to account for the effects of lensing to avoid biases in your parameter estimations of both individual events or populations. And how about LISA? So there was an estimate, but it was over 10 years ago, saying that there would be at most 4 strong lens massive black hole binaries in a 5-year observation window. Now, this very low number mostly comes from, the simulations that they use for the population of massive black hole binaries that generally gave a low detection rate. And there was more recently an estimation for MRISC, and that claims that you could have between 0 and 40 strong lens events in 4 years. Again, this range is mostly because of the unknown properties of the population of MRISC. So what we did in our work is mostly to recalculate these strong lensing rates from massive black hole binaries using more updated simulations for these black hole populations and the most up-to-date code, LISA beta code, to calculate SNR and parameters of these events. So regarding the populations of massive black holes, what we use are the simulations by Barrows and collaborators that they've been developing, over 10 years or so. And in a 2023 study, they do compare the different simulations that are available to pulsar timing array observations. And because there is, of course, a correlation between how many very massive black holes in the PTA band you would observe, those are related to the number of LISA black holes that you would observe, then this PTA information or PTA data sets a constraint on the viable black hole simulation that are currently public for use. So what we use here are these 6 simulations that are developed by them. Only one is what we call light seed, which means that massive black holes form in the early universe from the direct collapse of early population of 3 stars. And the other available models here, simulations, are heavy seeds, which means that the massive black holes form from a more massive object from the direct collapse of gas in the early universe. And these are the simulations that we selected, or well, these are some of the ones that they selected in the 2023 study as being available, as being viable, in agreement with PTA observations. And here you see the number of intrinsic mergers that each one of the simulations predict. And we calculate the number of detected mergers using the LISA beta code to calculate the signal-to-noise ratio and set a threshold of detectability of 8. And here you see that there's wild variations, right? So in the most pessimistic case, you observe 70 mergers in 4 years. These are values for 4 years. And in the best case scenario is like 38,000. So there's a lot of variation, and at the end, for the strong lensing applications, these unknown properties of the massive black hole sources is the biggest source of uncertainty. So in terms of rates, said in other words, you could detect either 1 every 20 days or 1 every hour. It's quite different. And the SNR, this is just one of the simulations for the POP3 for you to have an idea that these events that you would detect go up to quite high redshift, as you see here, above redshift 10. And some of the events could have SNR over 1,000, which are the blue ones. In this POP3 simulation, because it's light seed, the massive black holes tend to be less massive, and all of the gray dots are events that you tend to miss, that have SNR below 8, and you wouldn't detect. However, strong lensing actually helps in this case, because strong lensing typically causes an amplification of the signal. So some of these missed events that would be missed if they were not lensed, they could become detectable thanks to strong lensing. So here we apply these black hole population simulations to strong lensing, assuming that these events have a certain probability of being lensed by a galaxy. And we make some assumptions about the number density of galaxies to match current galaxy catalogs observations. And here's an example of more or less the rates of lensed events that you observe. So, for example, here we have 3 columns. And the first column, this one that says 1 detected, it means how many events in 4 years would have only 1 detectable image, because in a strong lensing, you can generate more than 1 image. In our model, you can generate 2. But the first image is the most magnified one, so usually that's the one that you will always detect. And the second column is the number of events for which you would detect actually both images. So the overall rates, again, of lensing vary mostly because of the unlensed rate variations. So in the most pessimistic model, basically you would detect less than, or you would expect less than 1 strong lens event per year in pink here. And in this other model, you could have, around 180 strong lens event in 4 years. So these are the main unknowns here. Now, what we see regarding of whether you would detect only 1 image or a second image, what we find is that it mostly depends on whether you have a light seed or a heavy seed source of black holes, because in the heavy seed cases, in all of the simulations, because these tend to generate more massive black holes, even without lensing, most of the events of the intrinsic mergers are detectable, which means that even when they are lensed, most of these events will have the 2 images detected, and then you could try to do some kind of correlation analysis to identify that these 2 images come from the same source and identify lensing. However, in the POP3 or light seed cases, because these are low mass events, it actually happens more commonly that you can only manage to detect one image. So this is, of course, a difficulty for the future, but LIGO or LVK and lensing analysis show that you could search for the second image as a sub-threshold event. And the other column that we have here is what we call boosted, which is what I mentioned before, that without lensing, you could have events that are undetectable, but then thanks to strong lensing and the amplification that comes with it, they do become detectable. So this is the number of events for which this happens that we call boosted. And for heavy seat simulations, this is not really a thing. I mean, it's not really relevant, as I said, because most of the events are always detectable. But for light seat simulations, this POP3 one, this is important. And here is a more concrete plot for the SNR that you expect for each one of the two strong lens images. So here on the left, we have row plus, which is basically the magnification and SNR for the most magnified image, which is also the one that arrives first. And this is for the second image. So, I mean, from here, this is the number of events that you could detect in this simulation that are strongly lensed in 4 years. And of course, what you see is that here for the most magnified images, there are events for which the SNR is over 1,000. And there are some gray triangles here that show basically cases for which you would miss the second image, but not the first one. The first image would be detectable in this case. So just to give you some quantifications, so for this type of simulation, but it's true for all the heavy seat simulations, for less than 10% of all of the strong lens events, you missed the second image. But however, for the light seat model, it's more common that you only see the first image and the second one remains below threshold. So for 60% of the strong lens events, you would have a missed second image. So here's a summary. We also have more information in our paper about what is the time delay expected between these different images. But because of time, this is my summary that you can read off. But maybe I just want to highlight 2 points. One is that strong lensing or lensing in general is unavoidable. It will happen at some point. In the case of LISA, the only question is whether we detect enough events for at least one or a few to be strongly lensed during the mission. And the other thing that I want to emphasize is that there is a LISA Cosmology Working Group collaborative project now happening on a strong lensing related to this, but mostly focusing on now doing parameter estimation. So I guess if you're interested in this, you can contact some of the coordinators. Thank you.
All right, thank you for an excellent talk, and we do have time for some questions. All right, go ahead and go to the microphone, and let's make sure it's definitely on so that Macarena can hear you.
Can you hear me? Hello?
Can you hear Shane?
Yes.
Okay,
Thank you, Macarena. That was great. You said it right at the end, but I was going to ask about the time delay distribution. I mean, these are all randomly generated, so this is all some function of the misalignment angle, which affects the time delay. So how many sims did you did, and what range of time delays do you see for all the events that you're making in these catalogs?
Yeah, let me see if I can manage to, because I have one, I mean, if we have enough time, I have one like backup slide with one plot that maybe can show. Do you see?
Yes, yes.
Yes.
Do you see this? Okay.
Yeah.
So, yeah, so the thing that is like absolutely random, as you said, is like the alignment that between sourceless and observer that is completely arbitrary. But here you have encoded information, for example, about the redshift of the sources and the redshift of the lenses that I didn't discuss much here because of time, but we do assume that the galaxy lens population matches galaxy catalog observations. And most of the heavy seat models tend to have similar curves. as you can see here, they fall, I mean, the most likely values are several months. But of course, they are quite wide, as you can see, for the distributions. And we simulate many of them. I mean, we do like 1,000, and then we just divide by the correct number of rates to be able to make quantifications of what to expect in 4 years or 5 years or so. But we make many of these. So all of the values that we show here are typically like means of what we expect.
Okay. All right, so I have a basic question, which was, you were talking about events that might get boosted that otherwise would not have been detected. I believe, looking at your numbers, that it was a small number in terms of changing our actual detection rates. I think mostly what you're concerned about is that the parameters we measure might be altered by the lensing in the first place, but if I've got that wrong, please clarify.
No, this is indeed true. So for all the heavy seed simulations, the number of events that are detectable only because they're boosted by lensing, it's irrelevant. This is relevant for POP3, so I guess we'll have to see, how many events actually do come from light seed simulations. I mean, from light seed sources. But yeah, part of the work that we're doing in the collaborative project of the Cosmology Working Group is do this parameter estimation, basically to see whether there might be any bias, especially if you detect only one image, the magnification might make you believe that it's just closer, for example,
okay,
or more massive.
All right, well, thank you for an excellent talk, and we'll thank our speaker one more time.
Thank you.
Okay. So we're going to go ahead and switch to our next talk by Bernard Kelly.
Hello. Okay, that works.
Yep, that sounded good. On direct collapse black holes.
Okay, well, thank you very much for being here. Start this off, because I'm rotten at time estimation. So thanks for being here. This is kind of a progress report on a project I've been doing with some colleagues at Hofstra University and University of Idaho and a few other places related to direct collapse black holes. So it's a progress report, but not anything very exciting at the end, I'm afraid, but we'll get there. So direct collapse black holes, you actually heard a little bit about it in the previous talk, but it's one of the possible ways that you might actually get a supermassive black hole in the early universe, or at least a good starting seed for it, because black holes, there are ways you can get black holes, and you can start with stellar collapse, and then a set of mergers / accretion, and try and build yourself up, but it's difficult to get to the masses that we know must exist in the early universe. So we wanted to look more at this from a, let's say, I'm going to say quote-unquote realistic starting point, but that's debatable in any way. But there's going to be a numerical relativity component of this, which is where I really come in mostly. So we're interested in it both for population purposes, knowing about supermassive black holes that will develop, that will be relevant as LISA sources in comparable mass binaries or in MREs or whatever, but also possibly in case the actual formation event itself could be observable by LISA. It would obviously be a transient event, not like a long, drawn-out kind of binary in-spiral kind of thing that we like for most LISA and indeed LIGO sources. I'm showing on the right a kind of a crude set of waveforms produced in 2009 by Sidro and Hawk for a direct collapse simulation, but I'll come back to it because it's not that useful. But there are some other sources of approximate analytic waveforms, Lee, Benequista, around about that time as well, but nothing too sophisticated that we knew about. So our idea is, and I said realistic in quotes, not to start with a completely arbitrary kind of gas cloud or whatever and work our way down to the black hole. We wanted to start with something that was kind of realistic. So what's more realistic in the universe, except we don't have the real universe to play with, so we're talking about cosmological simulations and we have to trust who's doing them. But we're going to start with cosmological simulations for the very largest scales, kind of identify areas there that seem to be likely to collapse to black holes in a direct manner. Then follow them through some intermediate stages to kind of more intermediate scales. And then finally, when we have to resort to numerical relativity to do the actual strong GR that will give us an actual compact black hole with a horizon and producing gravitational waveforms itself. So that's what we want to do. At the cosmological scale, there are lots of different cosmological data sets to choose from produced by different groups with significant computational resources. They use codes like ENSO or FIRE or several others I can't remember the name of, and then the simulations are so important that they actually save them in huge data sets and give them fancy names. So we were particularly connected with John Wise in Georgia, and he had been working with the Renaissance simulations, and they're about 10 years old now, so they're not the newest thing available. However, they're something we knew about. In those simulations, they're kind of mined for lots of different purposes, but in particular, for our purposes, John and collaborators identified several clumps, areas, halos in the overall simulation volume, where you could see halos that are likely to actually collapse to supermassive, or to at least some kind of massive black hole seed, because they don't have other kind of exit points due to the radiation environment they found themselves in and the low metallicity. They were deemed to be very unlikely to, for instance, fragment into smaller stellar objects. But so we want one large collapse. But I want to show the scale here, because these things are very large scales, these cosmological simulations themselves, and even the clumps are very large. The kind of standard mass of the clump is around about the million solar mass range, and they're spread over hundreds of parsecs per axis. And so that, if you convert to units of m, as numerical relativists tend to do anyway, that's like billions of m per side. And if you do a typical numerical relativity simulation, you might go out to like 1,000 or 10,000 or even possibly approaching 100,000 in your volume on each side. So we're like several orders of magnitude smaller scale, what we can do for an NR simulation, than we'd have to be able to do for a Cosmos simulation if we just took that clump and put it in an NR simulation. So that's my very jumbled way of saying we can't put that in an NR simulation, it's too big. We'd all be dead and gone. So we have to have some kind of intermediate stage, and that's why I'm just going to go through here. We need some kind of intermediate stage to bring us from our cosmological kind of halo thing down to something we can attack with NR. And the way we want to do this is using the MESA code, or MESA libraries. It's very mature stellar collapse code. It has very sophisticated handling of all the processes you'd expect in the sun or main sequence stars and things leading to such structures, nuclear interactions. They can do different kinds of things. They don't always have hydro in them, but so we've been using some hydrodynamics, but there are other ways of going about it. They are Newtonian gravity. Sometimes they have little tweaks where you can put in relativistic corrections. They call them relativistic or GR, but it's, first order kind of approximations. They are 1D codes. Or this MESA is a 1D code. I think other rivals tend to be 1D codes as well. They can accommodate rotation, sort of, but you do have to, there are restrictions on what they can do. But at the end point in this MESA simulation, you take something large and puffy and young, and you contract it down, follow standard processes, and you end up with something much more compact, and it'll output profiles for you. And you get many, 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 many things it wants to tell you. We're not interested in most of them because it's details about the nuclear component. In NR, generally speaking, we're not talking about individual species anymore. We just think, hey, give us a fluid and give us a density, pressure, temperature, internal energy, that kind of thing. And that's about all we can deal with. And velocities, if they're relevant. Okay, and then for the NR point of thing, which is where I come into it, I'm just using the Einstein toolkit. It's a standard code, Cartesian, kind of deals with kind of, it's good for comparable mass black hole simulations or binary mergers, that kind of thing. We use the BSSN or BSSN-OK formulation of Einstein's equations to solve the space-time metric it involves. If we're evolving fluids as well, in hydrodynamics or magnetohydrodynamics, we use the Illinois GRMHD code, which is produced using the Grail libraries. And I've got these cute pictures here because Baikal is produced by using this code generation mechanism called NERPy+, and that's a NERPy, the seal, the mascot. And Zakatin wanted me to tell you that Grail isn't generated using NERPy, and it has its own mascot, which is Tim the Enchanter from Monty Python and the Holy. You get the idea. Anyway, the input to this is, for an NR simulation, you don't just have the fluids, you also need the metric quantities. You need your first guess. So you get all these fields, both for the actual fluids and the metric, and the end result, you hope, is a final object which has a horizon, has horizon-derived quantities like mass and spin and so on, and also the gravitational waves produced when this thing evolves. Or produced. Okay, so how do you go about doing this? Nothing we've used before at the other scales actually knows anything about metric. It just assumes a Newtonian background, which might as well be flat space. If we want to use this, we have to have some specification for the metric. A very common one to use for stellar collapse situations is what's called the Komatsu-Haraguchi-Hachizu, or KEH formulation. It goes back to the late 80s. It's been implemented in the code available to us by Sturgiulis in the mid-90s. And it just assumes that you have this kind of stationary metric, and I'm going to come back to that, of this form where you have the few free potential parameters or potential functions, those 4 Greek letters, and then you hit it, thank you. You hit it with 3 free parameters, 1 the central density, and 2 other things related to rotation, kind of the ratio of your polar to equatorial radius. It's a measure of rotation and kind of stationary stars, and also differential rotation parameter. And you solve all this, it gives you a set of coupled elliptic equations, and it spits out all these things for you. But there are drawbacks. And it assumes you're using a polytrope, which is a good approximation for main sequence stars, kind of 4/3-ish. It assumes a very specific type of rotation law, which I don't expect you to kind of make much of this, but it is a restriction on what kind of rotation it knows what to deal with. The biggest restriction is, I said it's stationary. So it's for people who used to kind of start on a stationary star, and then if you want to induce collapse, you have to kick it, which is not really what we're dealing with. However, it's something we can try to use. So we can try, I showed you the Sidro and Hawk waveforms earlier, I'll just go through it. We can do the same thing that they did. We can start with their initial data, which was one of these KEH sets, no kind of information about cosmological scales or anything like that. We start out with a lapse function, which is kind of a measure of the curvature of space-time. As it's evolved, it starts nearly flat, kind of dimpled in the center. As the evolution proceeds, it drops and drops and drops and drops, and it gets low enough, that's about when you see a horizon forming. Simultaneously, the density starts out kind of curved there in blue, and it gets sharper and sharper and sharper. And that's when a black hole forms, and you can show for the same simulation, black hole forms at this time in code units, and this is the mass, and it gets larger and larger. I'm actually showing 2 different measures of mass, and you get a waveform out of it at the same time. If you have uniform rotation, it looks like this. If you have differential rotation, you actually have more angular momentum in the system, so the 2 mass measures are different because one contains spin energy and the other doesn't. Anyway, but this may not be the best way to do things. Anyway, but I'm going to show what we can do with this. So if we want to take our initial data and plug it into this, we have to be able to give our 3 parameters. It's trivial to give the central density. It's, you can infer a kind of a radial, you can infer this ratio and this A from the rotation parameters from MESA, and you can say, okay, I'm going to assume it's a polytrope, and MESA actually will give you an adiabatic constant gamma 1 that you can use. You run this through the data, and you can actually get an evolution. But I just want to show you one thing. This data set I'm going to use now, this actually comes from Harrington, not directly from our own work. This came through MESA in a particular simulation. We can't really say use this kind of situation or assume you're polytrope and assume kind of plug stuff into KEH unless we can identify the region to which it applies. Here you have a very nice kind of very well-defined core region here where there's very constant specific entropy, very constant mean molecular mass, and the gamma 1 and so on. You can say, okay, well that's an obvious cutoff, so we'll use this central region for our solution, and then we'll tie something onto it at the end. If we do kind of more realistic profiles, we actually get something different when we try doing our cosmological things. This is not particularly mature, but this is a typical endpoint for cosmological simulation. Sure, we can get a central density, but now there isn't an obvious cutoff to say, here's the core, here's the core, here's the core. It's kind of got step function behavior. Any of these step functions, even the outermost, only contains like about up to 10% of the total mass of the system. So this is a drawback. But I'm going to show you what happens with the easier one. We put it into our KEH code initial data, we run it, and we run it for a while, and I cut off a little bit of this because it's just very long and nearly constant. This is the lapse. It's very high, and then it drops down. It actually collapses. We get a horizon. Here's what happens to density at the same time. And that's this telling me that I'm out of my own time. I'm into question time. Okay, thank you. Okay, thank you. So this shouldn't be good enough because there's too many assumptions, both because of the stationarity assumption of RNSID and this issue about identifying core regions. So I thought, well, perhaps you don't need to do that whole thing. This data is hydro. It's actually kind of low density. It's very disparate, diffuse. Perhaps you can get away with just putting on an actual flat space. This is the metric of Minkowski space, flat space-time with nothing in it at all. If you just paint that with the hydro data from the evolution, perhaps that'll work. It doesn't, at least for us, unfortunately. So this blue thing is what I showed you before. This is the lapse collapsing down. If I just use the RNSID, which is the more complicated initial data equations, if I use this thing I call FSM for flat space MESA, which is a fancy way of saying I'm using flat space, I get something which starts dropping down and then bounces out. If I instead try doing something else and being a little more clever with them, putting little aspects of the metric in, it still does the same thing. It always bounces out. So right now, we don't have something that works without using the full RNSID, the full kind of elliptic equations assumption that went into that stationary black hole and perturbed, or stationary star solution. So that's what we're dealing with. I don't really have time to talk about this, but we've kind of speculated about how far we should put MESA before we give up. How far can we push MESA into the strong field regime and to make it more likely that it's going to overcome the standard kind of hydro shocks that cause this bounce? So we can get it as far as an infall velocity of about 12,000 kilometers a second, which is way past where most people stop their MESA runs. We haven't tried that yet in full NR, but we're hopeful. So I don't know. I'm just going to summarize here. So we have a technique, a strategy. It doesn't work yet. We have things we want to do technologically, which are kind of straightforward, use a proper equation of state from MESA, and actually put a proper constraint solver instead of just having flat space. But we also have just a lot of open questions about whether we really know what should collapse. There are various criteria I didn't go into, which this data satisfies, but it's still not collapsing all the time. And can we push MESA far enough to get us into this regime? Okay, I'll stop there. Thank you very much.
Alrighty. I see someone approaching the microphone. I saw Kelly move first. So go ahead, Kelly.
Sorry. This is really interesting about how to stitch together three very, very different codes. My concern is...
Is that microphone on? Let's double check.
Hello.
Okay.
Yeah. My concern is the MESA part, actually.
Yes.
I taught stellar astrophysics, which now all of a sudden makes me feel like I'm an expert in it, which I totally am not. But my guess is that from Renaissance, you took a metallicity of the gas and maybe the chemical, the abundances that were available in that gas, and you put that in as initial conditions, and then you just let Newtonian gravity go. I am confused about why all of a sudden you have this core, which implies maybe there's fusion going on, which is really not how I thought the direct collapse black hole scenario is supposed to work.
I am using core like a person who shouldn't be using core. Please do not take the word core too seriously.
Okay.
Essentially, this is a region, I'm calling it a core because it's a region where I can see kind of predictable behavior that will map well to the assumptions that I have about like a fairly constant adiabatic constant. You know what I mean? Over spatially. So I'm looking for a boundary.
Yeah.
But it probably doesn't mean core in any useful sense. But that said, also, I didn't name drop appropriately.
No, you're good.
Our MESA expert is Sarah Gosson, who's currently at Hofstra University, would love to have been here but couldn't be.
Got you.
And she would be able to answer more about the actual assumptions made.
No, I got you. I do suspect that it's maybe MESA's being used in a way that is beyond its capabilities.
It's off-label. I think a lot of this is definitely not. This is not your standard. Just like the RNSID thing is off-label.
Hey, it's science. This is what happens. But maybe we can talk about other things.
I would love to talk about other options. Thanks.
All right. I think. Okay. Let's thank Bernard again. Our next talk is by Kaitlyn Szekerczes. She's from Penn State. By the way, Bernard got his PhD at Penn State. So did I. And she's from Penn State. And as far as I know, that's a coincidence. But welcome. Okay, so we're going to talk about galactic imposters, electromagnetic confusion, and the LISA error box. And I'm going to do this at 5 minutes and this at 1.
Yeah. Okay, awesome. You all can hear me, I assume? Great, okay. Thanks. I'm Kaitlyn Szekerczes, and I'm really excited to get to talk to you today about galactic imposters and the electromagnetic confusion. Okay, so the first question we could ask is, why do we care to do multi-messenger astronomy with massive black hole binaries? Now, I think we've heard about this a lot throughout the conference, so I'm not going to go through this in depth. But I think it's always important to reiterate the first point in that the more messengers we can obtain for a single event, the more we learn, right? So in context, we get a detection from LISA for massive black hole binary. If we can obtain EM observations as well, we're just going to get better constraints on the system parameters. Now I want to jump to our point 4 here. And obviously it's going to be very challenging, but it would be really exciting if we could get pre-merger electromagnetic or EM counterparts, because this would allow us to get time domain observation throughout the spiral and merger, and most importantly, give us plenty of time for follow-up, specifically spectroscopic follow-up, which would just have rich data. But of course, there's a lot of practical challenges if we want to do this. The first that we've heard about a lot is that just, the localization region of LISA prior to merger is just massive, right? So this is a 10 to the 5 solar mass massive black hole binary at redshift 1. And here this is sky localization leading up to merger. And so 1 month before merger, this localization region is greater than 100 square degrees. As the system evolves, spends more time in LISA band, this localization volume shrinks. And 1 hour before merger is less than 1 square degree. But this is still quite big, and if we have some detection, we want to find the EM counterpart, it's going to be really challenging. To put some numbers and some context in here for you, Carrie Drake did a study with very similar masses, looking how many SDSS galaxies may be a potential host for a massive black hole binary like this. And 1 hour before merger, she found still tens of galaxies, and that's just a lot to parse through, right? So this is still going to be a challenge. Now there's also the potential for EM confusion. And so what we're showing here is this is power accretion rate as a function of frequency with respect to orbital frequency for 2 different massive black hole binary scenarios. And I want to draw your attention to 2 specific things. The first is that there's a range of frequencies here at which the massive black hole binary may be photometrically variable. And the second is that there's multiple frequencies here contributing. It's not one frequency alone, which means it's challenging to predict what this EM signal is going to look like. I think we've heard a lot about this. But this leaves room for the potential that other objects may look like how we expect the massive black hole binary looks. Okay, so over here on the left, I'm showing 2 different light curves. The top is a observed black widow pulsar binary, and the bottom is a simulated massive black hole binary light curve. And the idea here is that they're qualitatively quite similar. So LISA detects a gravitational wave from a massive black hole binary. With the telescope, you go to search for the EM counterpart. We're looking for objects like the bottom light curve. We find many objects with light curves like the top. And it's going to be very challenging to be sure that you found the EM counterpart properly corresponding to the massive black hole binary. Right? So this means potentially there are many imposters out there looking like how we expect the massive black hole binary is going to look photometrically. And again, for any astronomers out there, let me throw you some numbers. Okay, so if we assume that a massive black hole binary looks like a quasar, say we have a 10 to the 6th solar mass quasar creating at Eddington luminosity, redshift 1, it's as bright as a CV 4 kiloparsecs away in the galaxy, where CV is a cataclysmic variable. Right? So these brightnesses are quite comparable at 23rd and a half magnitude for that example. And now to make this even more fun, we're essentially surrounded by confusion, right? We're in the galaxy surrounded by objects. So this is just a cute little cartoon to kind of really drive this home. So say LISA detects a massive black hole binary in 2 different locations. The first is along this pink dashed line of sight, above the disk, maybe through the stellar halo. A lot of objects will be on the line of sight, but maybe not that many, so some will be projected. Now conversely, if we were looking along this green dashed line of sight, you're looking maybe through the disk, very dense regions of the galaxy. Lots of objects are going to be along your line of sight. Many will be projected onto the error box, meaning maybe some there will have signals like what we expect for the massive black hole binary, and this is where our EM confusion can come about. And this brings us to the primary question we're interested in my project, which asks how many galactic binaries fall into the error box of a massive black hole binary with the potential to confuse us electromagnetically given their periodic signal. And so the way we go about answering this and trying to tackle this so-called confusion is through the following framework that I'll walk us through now. So you first begin with a model for a particular component of the Milky Way, the galactic bulge, maybe the thin disk, stellar halo, so on. You take this model, you plug it into a population synthesis code, simulate out the binary population. You then count up all of the binaries that have orbital periods consistent with the massive black hole binary in the LISA band. And then, of course, the most important part is which ones are observable, because only the bright ones are going to matter. These are the ones with the potential to have this EM confusion, right? Go back and do with the rest of the Milky Way, and yay, you're done. Okay, so for the sake of this talk and going through the framework, I'm going to be focusing on the galactic bulge. But first, let me introduce you to our imposter population. So these are the systems that fall into the LISA band. I'm showing two different suites of histograms here. The solid ones are from all of the Milky Way, all of the components. And the dashed histograms are just from the galactic bulge alone. As I mentioned, that's going to be the focus of the remainder of this talk after this slide. Okay, couple things I want to walk us through and draw attention to here. The first is that we're binning according to octaves or factors of 2 in orbital frequency. And this is because, as I mentioned earlier, there's a range of frequencies at which the massive black hole binary may be photometrically variable. We're not sure exactly which one it is. So this is kind of like an uncertainty region. And so if we bin according to that, you're counting and accounting for all of those binaries within that range. Okay, so the three big imposter types that we find, the first are binary white dwarfs. I think no one here is shocked. We know that these are very numerous in our galaxy. These are going to be very important sources for LISA, so no surprise there. And then in green, we also find many white dwarf main sequence binaries, where if these are interacting and transferring mass, these are the cataclysmic variables. These are our CVs. And then to a lesser extent, but by no means negligible, we also find neutron star white dwarf binaries. Okay, and again, we're going to be focusing on our dashed histograms here. So now what we want to do is we want to estimate how many may actually be projected onto the error box. We're here again, here are galactic bulge binaries. I've just removed the rest of the Milky Way. Okay, so over here on our right, this is what we've been calling the LISA localization beam. This is a 3D beam directed at the projected error box, so your error box is right here. And what you do is you count up and add up all of the mass enclosed within this beam. So if we're considering just the galactic bulge, just add up all of the imposter mass from the bulge. And now to get the total number projected, you take the product of these two quantities. Okay, and that's exactly what we've done here, so I'll walk us through this plot a little bit. This is the total number projected onto the error box. And we've swept the LISA localization beam around in longitude, so around in L. And we're considering two different realizations for galactic latitude. B of 0 is straight into the plane, densest region. B of 30 is 30 degrees above. And obviously, since we're just considering the galactic bulge, when you look away from the center, numbers fall off. But even for 30 degrees above the plane, we're finding greater than 10 to the 4 binaries may be projected onto this error box. But of course, at this point, we haven't considered things like extinction or their inherent brightnesses, so this is just total number. So what we want to do next, of course, is to ask, how many are going to be observable. And the way we do that is through the following. So we take the binaries that we just formed, we spatially distribute them, so given that we've been focusing on the galactic bulge, distribute them according to that. And then we use 3D dust maps to estimate their extinction given where they're placed. We then assume a typical luminosity given what kind of source it is. So like if it's a CV, there's a typical luminosity we assume for that. And now given luminosity and extinction, we can estimate their apparent magnitudes. And then to estimate how many are going to be observable, you assume some sort of magnitude limit for a particular survey, and everything brighter than that are the ones that may be observable, right? Okay. So here is a super preliminary look at that, where our top row again are just all of our galactic bulge imposters split up by binary type. And the bottom panel is, we've placed them, assumed some sort of extinction, assumed some sort of luminosity, and then estimated their extinction to get apparent magnitudes. And these are all the ones brighter than. This is for a single visit R-band LSST magnitude limit. So obviously, not all of them are observable. This makes sense. Not all of them are going to be very, very bright. But the numbers clearly don't fall off to 0. So as like a first glance, it's important to note that some of these may still be projected onto the error box. Some of them may still be bright enough to be observed and have this photometric variability to worry about. So first glance, okay, still a problem. Okay. So where are we going next in terms of taming this so-called confusion? As you saw, I was able to spatially distribute the galactic binaries from the bulge, but I haven't done this for all of the remaining components. I'm actively doing this now, so I'm gonna wrap that up. And as I mentioned, what we did for the luminosity, we assumed some typical luminosity, but we're gonna do a lot better. We're gonna go back and look at what the systems are doing, how their mass transfer rates are to get a better estimate of their corresponding luminosity given what each individual system is doing specifically. This is inherently going to update the apparent magnitudes and obviously change how many are observable. And then something also I'm interested in is how is this distribution of observable imposters vary across the sky from all of the components together, also in imposter type. I think that would be interesting. Okay, good. I'm giving you lots of time. Okay, and so I'll leave you with my key takeaways here in that we know that many Milky Way binaries are going to occupy the same frequency space as massive black hole binaries, and some of these are going to be as bright as a massive black hole binary and vary periodically in this same period range. But our saving grace is that not all of them are going to be observable, so we'll see how big of a deal this is. But please stay tuned while we wrap up this project and have more concrete numbers for you. But I thank you very much for your time, for staying until the end of the conference, and I'm happy for questions.
All right, thank you. And for those of you who have just joined us, we only have 4 talks in this session, so we have been permitting a little bit of extra time per speaker, but that was our 3rd speaker of 4. And oh my goodness, we've got lots of questions. Okay, we'll go ahead and start with Oliver.
Yeah, maybe I'm missing something here, but you're looking at optical brightness, right? So wouldn't it be extremely helpful to look at the spectroscopic information of these things, because they are all in our galaxy and the massive black hole very likely not?
Yes, excellent point. So I don't know if his mic was heard very well, but he asked, isn't it helpful to look at their spectroscopic observations? So absolutely. The idea here, though, is that we have a detection from LISA. We don't have a lot of time prior to merger, and we want to follow up as soon as possible. Spectroscopic observation takes time. So if we don't have these observations in advance, we might not have enough time, but leading up to it, characterizing and getting a catalog of these potential imposters with spectroscopic confirmation that these are binary white dwarfs, these are whatever, these are not massive black hole binaries, absolutely. And that's very much something we're interested in leading up to this. But this is kind of like a worst case scenario of, we haven't previously observed this object, what is it? Without a spectroscopy, it's gonna be a bit interesting. Thanks for the question.
Miranda?
This might be a kind of similar question. So to the idea, is this working?
Yeah. Okay. You don't have to use an Oliver height microphone. You can, wait, take it all the way down. Yeah.
There are people to help me 5'2" use a microphone.
Yeah. Okay.
Hi. Maybe a similar question. But so if you were to build a survey and be this is what we would need to be we need these observables minimum on the Galactic Center, so we at least have this kind of catalog to narrow down, make it easier when we're doing a desperate search. What would you want? If you get the observing time in a perfect world, what would you want?
Oh my gosh, what a question. Okay, well, obviously we need high cadence because these are short period binaries. So often people are like, oh, LSST, is that gonna do it? I mean, yes, but LSST cadence is on the order of days, right? So one needs a lot of observations to fill in these periods. So we need a short cadence, and definitely getting their colors would help. And of course, their spectra would be just the ideal, but you gotta get a lot because there's a lot of binaries here, which is why we need to figure out how many and where to look to get that catalog in advance. Thanks.
All right, Jake? You can adjust the height of the microphone to the excessively tall setting.
I think I'm still, with your answers, I think I'm still contemplating my question, so maybe we'll...
Okay, yeah. Excellent, thanks.
Okay. But similar to the spectroscopy, I would imagine even just having imaging would help, because if you've got a spatially resolved galaxy, coincident with your transient, then you've got a good hint that it's extragalactic. So there's a lot of other information that we can use. Okay. Okay. All right. We will go ahead and thank Kaitlyn. All right. And while we're transitioning slides, I'm supposed to make an announcement. If you do not want your name tag, there is a box outside. We will reuse your name tag. And I would actually amend that if you don't want this beautiful lanyard, please also, there are people that wear badges every day and will use the LISA lanyards, but you are welcome to keep the lanyard. But if you think you're not going to use it, put it in the box and we will make sure it gets used. Okay, so we're coming up on the final presentation. I realize there's supposedly stuff going on in other rooms at this conference, but you're in 6C. So this is where it's at, okay? All right, yeah, okay, let's get excited. And Ryan has been waiting all week to give this talk, all right? So this is my challenge to you. I want your full attention. Remember what we said at the beginning? Smile at Ryan. It's not easy being the last speaker, okay? Okay, there we go. All right, okay. All right, I already got a lot of applause. So we're gonna give Ryan 1 extra minute, which we've been doing for all the speakers in this session because we only have 4 speakers. We're trying to give them a little time, but be respectful of the only couple of people who are still up in Europe watching this presentation. So without further ado, what can LISA and LIGO teach us about the origins of light-intermediate mass black holes? Take it away, Brian.
Awesome. Can y'all hear me on the mic okay? Perfect. I want to thank y'all again for coming to the very last session on the very last day of this talk. I know this is all about massive black holes, and I would love to end it all with a bang, but we're going to end it with maybe a little bit of a whimper, unless you work with LIGO, and then it is still a bang, because we're looking at the most massive sources that LIGO can see, these light-intermediate mass black holes. So my name's Ryan Nowicki, and I'm a PhD candidate at Vanderbilt University studying these crazy little objects. So the first thing I want y'all to know is that LVK as we've continued to run the LVK and collect more and more observing runs, we've discovered this population of hundreds of solar mass-sized black holes. This burgeoning population that we continue to see really challenges our understanding of the formations of these systems. For a few name drop moments, GW 190521 was the first one to really push over this 100 solar mass boundary, and GW 231123, recently published last year, pushed above 200, and really is pushing the limits of what we can understand. One key fact I want you to know is there's this idea of the pair instability supernova gap, wherein in traditional stellar collapse models, when you have a star more than 60 to 130 solar masses in size, it collapses, it dies, it does not leave a black hole remnant behind. And so we expect from our models that there should not be black holes of this size in creating binaries, creating gravitational waves. And yet we do see these. So for example, in this plot, you can see highlighted GW 190521 and GW 231123, both existing in this gray band gap. And then a bunch of other candidate sources people have done with archival searches specifically targeting these events. And so because these things kind of exist in this gap and challenge our models, we call these light intermediate mass black holes. And so to understand a bit more about formation channels, again, this traditional star collapse model is one that is challenged by these systems, but there are other ideas. There's an idea, we often think about hierarchical mergers. If we could take maybe a bunch of smaller stellar collapse black holes, push them together, and get more and more mergers, they can get more and more massive and potentially occupy this gap. And so for one, people think a lot about these in dense cluster environments. These could be globular clusters, nuclear star clusters, or just dense baby open star clusters that are forming. And you can push these black holes together to get massive sources. Alternatively, a lot of people who have been working with Savick-Ford and Rubartos, they're thinking of this AGN formation channel, wherein gas in the AGN disk can fragment, form stars, collapse into black holes. And as these black holes migrate through this disk, they interact, merge, and grow to these massive sizes. One key thing to understand about all these different theories, as these all pop up to try and understand these sources, is that the information about their evolution is encoded in their spins. The mass tells us they got here, they're big, but the spins carry the history of their evolution. And so in order to disentangle where these sources are coming from, we need to understand what are their spin properties. And so we can look to understand those with parameter estimation. So why am I talking about these sources at a LISA talk? Well, lucky for us, these massive, massive sources are also coincident LISA sources. LISA and LIGO together can observe these sources and provide us each differing information about these sources that we could use to get a better picture of where they come from. So how do we do that? We use multi-band parameter estimation. There have been several talks this conference about parameter estimation. How are we trying to measure the parameters of these systems? And in the same way as we do multi-messenger science, getting more information from different channels, we can also look at just different bands of the gravitational wave frequency to understand these systems. So for these systems, I've created this little plot here of these 4 example IMBH systems, light IMBH systems, and you can see that their in spiral occurs in this LISA band about 4 years before merger. before eventually leaving the LISA band for several months to years, and then merging in the LIGO band down here at the higher frequencies. When we capture this, we get different information from both these sources. The in spiral can tell us more about the frequency evolution, the mass, and then the merger ring down phase in the LIGO can teach us about how much, they get more higher order mode information that can teach us more about the spin properties as well. And so while there's much work on building multiband pipelines out there, Szekerczes Wu gave a great talk about a coherent multiband pipeline on Monday, but looking at using archival searches in LISA for ET and Einstein Telescope Cosmic Explorer data. This work I choose to motivate with a LISA first approach, looking at these loud signals in LISA that might have a potential to be early warning multi-messenger signals that could distinguish between a gas-rich or gas-poor environment. And so this brings us to the real question of the talk, which is how well can we measure the masses and spins of light and intermediate mass black holes in the LISA, LIGO, and multiband? And can these, quote, formation channels be better constrained with multiband parameter estimation? And if so, by how much? So to do this, I construct two mock formation channels here. And for the simplicity of this work, we choose just simply an aligned spin and an anti-aligned spin configuration, the limits of which I will make clear in a moment. This first one, we have our two highly spinning black holes here. This is mostly like an AGN disk analog where coherent accretion can spin black holes up and align their spins together. Whereas the anti-aligned spin configuration, we choose simply to flip this direction of the secondary, whereas in like the isotropic spin distribution of a gasless cluster environment where everything is moving around might be more indicative of that. And so to create these two analogs, we can say how well can we distinguish these using a multi-band parameter estimation network. I'm going to go a bit now into how we sort of build that network and how we build our parameter estimation case. So for each of those spin configurations, we choose to create 4 mass cases from 150 up to 450 solar masses. The first of these two, the 150 and 250 mass cases, are representative of analogs of our GW 190521 and GW 231123 cases, respectively, sort of understanding how these sources might look in a multi-band environment. And then again, to motivate with the LISA first detection approach and understanding these systems, we inject them at scale distances such that we have a LISA SNR of about 15. This allows us to get resolvable sky localizations in LISA for these systems, and therefore allows us to make a simplifying assumption with our parameter estimation later. And again, these are the parameters of the systems and how these look for 4 years of evolution in the multiband in this characteristic strain plot. Again, then for our parameter estimation, we build a detector network. We use LISA in our LISA band, naturally. That's why we are here. And then for the LIGO band, we choose to use the advanced LIGO PSD curves using the Hanford, Livingston, and LIGO India configuration. And then we also use an aligned spin waveform model, IMR feed on D, because when we get to our parameter estimation methods, we choose to implement a wavelet domain algorithm for the LISA band parameter estimation. If you've been hearing talks earlier this week, the tea leaves are moving for LISA data analysis to move toward time frequency approaches to parameter estimation. And this is because time frequency parameter estimation techniques can more effectively compress our data and perform parameter estimation more quickly. And so we choose to implement tools similar to such pipelines. However, the implementation we had was limited to only working with aligned spin waveform models. And so we construct our injection set and use the aligned spin waveform models accordingly. Yeah, that captures the LISA band. In the LIGO band, then we also use something called RIFT. This RIFT algorithm has been used for LIGO pipelines before. It is a grid-based approach, and it implements extrinsic parameter marginalization. We marginalize over our sky localization and our distances and those extrinsic parameters to get a better sense of how the intrinsic parameters are evolving. And because we've chosen a sky localizable source in LISA, the vast majority of our extrinsic information is obtained from LISA, and I think it's appropriate that we can marginalize over this in our LIGO band parameter estimation to get more information for our extrinsic parameters. And then lastly, how we build our multiband is we stick these two things together. We say, how can we take our LISA posteriors from our parameter estimation, wherein we estimate and measure what the spin properties are in LISA, put those as limits on our LIGO parameter estimation, and put them together to get a sense of how these things are evolving together and how we could measure these properties together. So to get into our results here, this is a Violin plot distribution of our sources. It's representative of the fractional error of each source. So we take our samples, subtract the true value, divide by that true value. And this is just to normalize against the different mass and distances here. And the key takeaways I want you all to understand is that the multiband is continuing to provides narrow constraints on the mass ratio and the total mass, as opposed to LISA or LIGO alone. Again, for the lowest mass cases, LISA performs more poorly compared to LIGO, whereas in the highest mass cases, LIGO naturally performs worse than LISA, as in more that there's less SNR for the higher mass cases in LIGO to lean onto and glom onto. Another big key takeaway I want you to take from this plot is that the individual primary spin measurement here, this plot, the multiband is least likely to infer a close to zero spin for this highly spinning injected source system. It is more likely to be open to the idea that these spins are highly spinning, which is important for understanding the origins of these systems. For a more proper analysis, we look at the 2D posterior distributions for chi-effective and chi-1, which are our effective spin of the entire binary system and our primary spin of the black holes in these systems. We can see that for LISA, in our lowest mass cases, case 1 and case 2, the 150 and 250 sources, the posterior distributions of these systems kind of overlap on top of each other, and you get a confusion there between which formation channel of our anti-aligned or aligned formation channel did these sources come from. However, and then the inverse is true with LIGO, as in the most massive cases overlap completely, and we don't have a discriminating power on what the exact sort of formation channel organism this is for this. However, in the multiband case, we see that across all 4 mass systems, the anti-aligned and the aligned spin configurations are sufficiently distinguished from each other. And so that is this, and so we are able to have a better conclusion on what sort of original formation channel these systems would have come from with that multiband information. And then we also looked at mass ratio versus the chi-effective distribution, and we can see that LISA here is doing a very good job of distinguishing these sources even on its own. LISA is a very powerful parameter estimation tool. 4 years of data in the LISA band will give us very strong constraints on these systems, but even still, they have these wide stretches of the posterior in the chi-effective space, and then with the multiband, we're able to narrow that down much further and have a much more precise measurement on the parameters because of that additional larger information from LIGO. And so to conclude, I want to have a few key takeaways, is that light MBHs are these ideal multi-band parameter estimation candidates. We can get the most information out of these sources by using both detector bands. LISA is really capable of improving our constraints on sources like GW231123 and their massive cases. And so as such, multiband is very, very promising for constraining the formation channels of these sort of light IMBHs that challenge current formation channel models. So thank you. Questions?
All right, we do have time for questions. Good job, Ryan. All right. And please do adjust the height of the microphone if you need to.
Hi. I have a very naive understanding of stellar mass binaries, so equally naive question. What are the chances that these are remnants of a hierarchical stellar mass mergers in nuclear star cluster or something like that?
Sorry, I'm gonna repeat the question back to you because I think I missed a bit of it.
Yeah.
You asked what the probability was that these would be from hierarchical mergers in nuclear star clusters?
Yeah.
So for my injection set, it is entirely a naive assumption of just these 2 candidates. I don't know an exact numerical probability that we will see things specifically in nuclear star clusters as opposed to a globular cluster or something else. It's definitely a high likelihood that such a dense environment would have interactions between compact objects such as that and produce such sources. So I would love to do more research and get back to you on that.
Yeah, and I don't know about the star clusters thing, but I know that there's a lot of LIGO work right now on hierarchical population studies, and they're able to take spins and such and figure out that a lot of these more massive objects should be like 2nd generation mergers, which would be basically a hierarchical merger. So that was not a naive question, that was a great question.
It was a very great question.
Yeah. So, okay, go ahead, Shane.
Brian, can you show me your violin plots again?
Absolutely.
At the risk of being a heretic, I don't care about spin, but your luminosity distance really bothers me because the true value is far from everyone.
Yes,
Okay.
and I have
Thank you.
an extra slide here for that. So I'm so glad you asked. Another reason we motivate the extrinsic marginalization with the LIGO band posteriors is because the LIGO extrinsic constraints end up worsening our multiband constraints based on how we constructed our multiband. So I imagine I think this is a problem with the construction of our multiband pipeline, because we aren't like enforcing exactly you have to fit within the LISA priors. We are allowing still some flexibility with those, just as them being a strong informative prior. And so what we see here is that LISA very confidently skylocalizes and distance inclination space effectively for these sources. But as we look at LIGO, the poor localization for these highest mass sources bleeds into the localization for the multiband. And so when you have the 1D parameter distributions, everything always is going to look funny. 1D parameter distributions are always a little finicky when it comes to actually drawing conclusions from these, which is why we choose to favor these 2D distributions.
What was case 4 again? Case 4?
Well, hold on here. You're not using a microphone.
Yeah, so the cases are by mass.
Thank you.
You said you were,
so
you were asking what the case 4 was, right?
I'm sorry, case 4 is so weird in the LIGO localizations.
Yes. Well, this is because it's 450 solar masses source frame, which means it's redshifted even further to a much higher sources. So this is like marginal detections in LIGO.
Thanks.
We are recording all of this for posterity. So
this is excellent.
There may not be very many people online at the moment because it's late in the day in Europe, but we're trying to use the microphone so that later on people understand what was going on in this room.
Thank you.
All right, go ahead.
Great talk. I was wondering in your, what I would just like consider to be like an ambivalent accretion environment, sort of like agnostic to like where these channels are coming from. Do you have any prescription or consideration for like gas stalling that would make these sources sort of sit in the LISA band longer? Perhaps includes the posterior.
We don't assume any prescriptions for gas stalling or the actual physical environments themselves. How we choose to create this injection set is simply saying, if we assume spin properties from a channel, what would it look like? It still is assuming vacuum evolution for our waveforms and all such properties. So it would be interesting to incorporate such behaviors in a future extensions project.
Interessante. Thank you.
Okay. I've got one other quick question while Kelly walks to the microphone, which is, so you said that you assumed some kind of scaled distance so you could get LISA signal-to-noise ratio of 15?
Yes.
So I was wondering how much you had to move those LIGO sources, like what it would have been at the distances of the real sources, or how much you moved them in the first place?
Yeah. So this is the parameter table here for these sources. So the distances are in this third column from the right. I believe for case 2, the 250 solar mass 231123 analog, the distance of 2.1 gigaparsecs is actually fairly close to the median estimate of LIGO. The source was very loud in LIGO, and so it's a good estimate. I do believe we did have to push the case 1 much closer to capture 190521 in that way. So there's issues there. But again, this is just choosing our optimistic LISA sources.
Great. Kelly.
Yes, I was just wondering how it felt to give the best last talk of the...
I feel free. I'm free.
Yeah. That's great. Miranda may still ask her question.
Yes,
their question. Yeah. No, it's okay, Miranda. Ask your question.
The best last question of the conference, exactly.
Yeah, no pressure.
If you've already said this, then I get to feel very silly. But so, have you tried this out for like a particular range of spin ratios for the? I do AGN channel, so I'm biased to the one case. But like, does it change the LISA LIGO alignment on stuff if you adjust the spin?
What do you mean by alignment, if I could ask a clarifying question?
The spin ratios, so like the spins for the primary and secondary.
Oh, if we adjust how they compare to each other, how that would affect the realization in LISA and LIGO?
Yes.
That is a great question, and something I'm looking forward to doing in the future. Again, we only examined these two spin orientations at the moment, so a proper population study is in the future work. And so I'm very optimistic to see how this compares for different orientations of spin and for also possibly population distributions for these two channels. So thank you.
All right. I think it is time to thank all the speakers and